The purpose of this section is to familiarize you with inclined planes, screws, and wedges. First, let's talk about inclined planes or ramps. A ramp is a plane or surface set at an angle from the horizontal. A typical use of a ramp is to raise objects that are too heavy to lift vertically. The load is pushed a longer distance along the ramp, but a smaller input force is needed. So the sacrifice here is distance, but the advantage is force. Thinking back to basic trigonometry, the hypotenuse of a triangle, or ramp in this case, is the longest side in a triangle. This is why the load is pushed a longer distance than if you were to only lift it up vertically. We see ramps everywhere. Some examples are a wheelchair ramp, ramp on the back of a truck, ramp on a city bus, or even a boat ramp. Let's take a look at how we can find the mechanical advantage of a ramp. In the case of inclined planes, we will actually be finding the ideal mechanical advantage, or IMA. We use the ideal mechanical advantage because of friction on the ramp. The ideal mechanical advantage is equal to the length of the ramp, or the hypotenuse of the triangle, divided by the vertical height. Just like mechanical advantage, ideal mechanical advantage also does not have any units. In this ramp, we can find the ideal mechanical advantage to be 10 meters divided by 2 meters, which is 5. Once again, we need to remember that the load force is equal to the effort force multiplied by the mechanical advantage. Let's take a look at an example. Here we have a worker pushing a box weighing 1,500 newtons up a ramp that is 6 meters long. We want to find the ideal mechanical advantage. To find the ideal mechanical advantage, we will take the length of the ramp and divide that by the vertical height of the ramp. Substituting, we have 6 meters divided by 1.5 meters, which leaves us with an ideal mechanical advantage of 4. This means that in a perfect frictionless world, we would be able to push a load that is 4 times heavier than the amount of force we apply. We have the same worker and box, but now we need to find the effort force that is needed if we neglect friction. In order to find the equation for effort force, we will look at the equation circle for load, effort, and mechanical advantage. Covering up effort force, we see that is equal to the load force divided by the mechanical advantage. Substituting in 1,500 newtons for the load force and 4 for our mechanical advantage, and remember, in this case we will use the ideal mechanical advantage, we see that the effort should be 375 newtons. In the next video, we will take a look at the remaining simple machines.